Good morning, class, and welcome to our continuing lectures on sustainable energy technology. In the past few classes, we have been discussing solar photovoltaic systems, and we will continue our discussion. In the previous class, we discussed the solar cell efficiencies, and we saw that the maximum efficiency of solar cells range from around 26 to 28% for silicon and around 30% for cadmium telluride, indium phosphide, or gallium arsenide type solar cells. And the efficiency curve for typical solar cell radiation for different semiconductor materials is given by this figure, with which we ended the last class. Now, this is the maximum conversion efficiency of typical solar cells. We will continue this discussion and see what other types of losses are there, and for a given solar cell module, what is then the final efficiency that we are getting under ideal conditions. So with that, we will start our discussion today. So first, let us look a little bit on the basic structure of our solar cell system. So if you see here, this is our kind of a typical solar cell module. It looks circular. So we will discuss this point later. That a given solar cell module will have multiple of these types of cells that are connected in series. So this is the front contact, and this is the rear or the back contact. Okay, you can see here N type is in front and P type is at the back or the base, it's called. So what you will be getting is electrons are flowing towards the N type and holes are flowing towards the P type. So if you see the flow of electrons will go through the front contact and go across the external circuit, and the electrons will enter through the back contact back into your solar cell device. So what this means is the direction of current is from the back to front contact. Okay. Usually what happens when you see solar cells in series is that the back contact of the first solar cell will be the front contact of the second solar cell, and so on and so forth. Okay. So front to back connections will be there, and then the solar cells will be said to be connected in series. At the top, this front contact connection strip is connected with this this electron collectors that are basically very thin rods that are collecting all the electrons and delivering it to the front contact system. Below these rods, you have the anti-reflection coating, which is stopping the solar light from being reflected from the top surface of your solar cell. After that, you have the NP and also P plus. So P plus means it's the doping concentration. The P type doping concentration is higher. So typically we call it you have very light doping is like N minus or P minus. Then moderate doping is NP. Then heavy doping is N plus, P plus, and then very heavy doping is N plus plus, P plus plus, etc. Okay. The typical dimensions are also given. This entire system is around 15 centimeter in diameter. Okay. So this front contact goes to the rear contact of the next series cell, and this is from the top contact of the previous cell. Okay. So this is how this system is given. So now here, what we are looking at is the approximate losses and efficiencies at each stage as the light is transformed into electricity throughout this solar cell. Okay. So for example, the top contact is basically collecting electrons, and these are actually metallic in structure and they are opaque usually. So what this means is a part of the solar light that is incident on the top side of your solar cell is not actually entering your solar cell but is getting reflected or absorbed by the opaque front contact. So the top contact obstruction, you lose around 3% of the incident solar energy. So you get a power loss around 3%. So the efficiency, the energy remaining percentage is 97%. Then you have top surface reflection. So this can be reduced significantly if you put anti-reflection coating in place, and we will discuss these points in a little bit more detail just after we go over this table. So if you have a good anti-reflection coating in place in the top surface, then the loss due to reflection can be minimized to around 3% of the remaining energy. So the energy remaining is around 94%. Now, at the bottom surface, as the sunlight goes to the bottom surface, what you want is a good reflecting surface at the bottom, so that any photon that hits the bottom surface is reflected back into your solar cell, so that it can again have a chance to get absorbed by the electrons to generate electricity. So rear surface reflection is actually an efficiency improving device, because if you have a good reflection system, some of the sunlight that would have been lost through transmission is being reabsorbed after it is being passed one more time to the solar cell. So you get a plus 3% increment in efficiency. So this 94% of energy remaining goes back up to 97%, because you are getting excess energy back. All right. So plus 3% efficiency gain is being obtained. Then you have the thermalizing, the transmission losses. That is, there are a part of the electrons that is not being absorbed at all because they have too low energy to promote an electron across the band gap. So that is around 23% for silicon. So there is a 23% efficiency hit due to transmission losses, where the photons have too little energy to get absorbed by the electrons and generate current. So then the efficiency, so the energy remaining goes to around 75%. So 97 minus 23, the energy remaining goes down to 75%. Then you have the thermalizing losses, that is the excess photon energy of the low wavelength photons, that is high frequency photons. Part of it is being lost as heat, and that is around 33% of the total energy of the solar incident sunlight. So you remove again 33% from 75, so you get around 50%. Okay. So remember, this is around what this is being is 33% of the remaining energy. Okay. So 75% was the energy that was remaining. 33% of that is around 25. So you get 50% of the total energy that was originally coming from the sun remains in your device after both transmission and thermalizing losses. Okay. So this now has reached 50% of the energy. Okay. Now you have something called capture efficiency. We will discuss this a little bit later. This is a small efficiency hit of around 1%, so it goes down to around 49%. Okay, 49.5, something like that. Okay, so it is this basically is giving you of the photons that do have enough energy to promote electrons, how many are actually being captured by the electrons to have this promotion. Okay, so that is around 99% of all photons that do have sufficient energy does excite electrons and get captured by the electrons, which get promoted into the conduction band. So the capture efficiency is around 99%. So this is around 49%, 49.5. So we are not giving the decimal places. Then you have something called the collection efficiency. So how many of the electron and holes that were created by the capture of the photons is actually being collected at the front and the bottom contact. Okay, so this is a very important aspect, because not all of it actually do travel to the front and the rear contact and get collected by the external circuit. So the collection efficiency is around 90% of the total electron hole pairs that are generated. For a well-designed solar cell, it can be lower also. We will discuss how we can increase the collection efficiency. And so 90% of 49%, you are getting around 44%. Okay, 10% of 49%, you can remove around 4% or 5% out. So you become 44% of the energy is remaining out of the total energy that was originally incident. Okay. Then you have the voltage factor. Voltage factor reduces efficiency because the open circuit voltage is actually less than the voltage across the space charge region. So you remember the voltage factor was around 0.8. So we are losing 20% efficiency there out of this 44%. So here we have again a large drop to around 35% of energy remaining. Okay. So remember that this is due to the presence of dark current and other currents that are created, which is decreasing the open circuit voltage that is available below the space charge voltage that is actually developed across the PN junction. Okay. Then you have the fill factor. This is the non-ideal case. So how the actual max power point relates to the idealized max power point given by the I short circuit current into open circuit voltage. Here its fill factor was around 0.88, so around 12% loss in efficiency is coming from that. So 12% of 35 is done and that is decreased. So you get around 31% of energy is left over. Okay. Then you have other aspects like recombination losses along the pathway. So all the electrons and the photon holes do not are partly recombining along the pathway. So there are recombination losses due to crystal defects, etc. So that is around 5%. So it decreases to 29%. Then you have series resistance and shunt resistance, which we discussed earlier also, that the resistance across the junction, and shunt resistance is due to maybe crystal defects that can create shortcuts for the electrons and the holes to recombine inside the cell itself rather than going through the external circuit. So these two have small power effects like around 0.3% and 0.1%. So it goes to around 25% finally. So a crystalline silicon solar cell under ideal conditions will deliver around 25% of the energy. Okay. So this is kind of the entire graphic of where the energy is being lost under which conditions. Okay. So let us discuss some of the designs that are used to minimize these power losses for a typical silicon solar cell. So our discussion is PV cell designs to minimize losses. Okay. So first is your top surface contacts. So a web of finger-like metal contacts arranged to reduce series resistance losses and allow light into the junction at the top. Okay. So you have a web of finger-like metal contacts that are specifically arranged to reduce series resistance losses and allow light into the junction at the top. Okay. These contacts are formed by screen printing process and placed in laser cut grooves to ensure good electrical contact. Okay. So these are usually generated by what is called the screen printing process and are placed in laser cut grooves to ensure good electrical contact. between the top surface and this finger-like metal contacts. Okay. Now, the next point is reflection at top surface. So, typical untreated silicon surfaces have reflection losses up to 40%. But thin film surface treatment can dramatically reduce the amount of reflection by producing destructive interference between light reflected from top and bottom surface of the film. The film thickness is designed such that the main reflected component are of equal intensity but differ in phase by pi radians, which implies a path difference of lambda by 2, where lambda is the wavelength. So suppose N0 is the refractive index of air. N1 is the refractive index of thin film, and N2 is the refractive index of semiconductor. Then for a given wavelength lambda, so given wavelength of incident light, okay, of light lambda, we should put N1, sorry, N1 should be equal to root over N0 N2, and film thickness T should be equal to lambda by 4 N1. Okay. So the idea here is, if you see Suppose this is your film. Okay, so this is your silicon. This is your film of thickness T. All right, your light is getting incident here. Part of it is getting reflected back. Part is refracted here, and again getting reflected this way, and rest is getting again refracted this way. Okay. So the idea here is these two light rays, have a phase difference of pi radians. Pi radians phase difference. Okay, and this happens because the extra path here that this wave light is traveling is lambda by 2. Okay, so this path here is lambda by 2. These two, basically lambda by 4, and this is lambda by 4. So together this extra path is lambda by 2. So the phase difference between this light and this light is pi radians. Okay, so this is your N1 is the refractive index of this thin film. N0 is the refractive index of air, and N2 is the refractive index of silicon. So to ensure this point, we need this ratio. For a given wavelength lambda, N1 should be the square root of N0 into N2, and the total thickness will be lambda by 4 N1. Now this is only for a single wavelength. So for solar broadband radiation, we can show that choosing N1 equal to 1.9 and T equal to 0.08 micrometer, that is 10 to the power minus 6 meters, can reduce reflection losses to 6%, and multiple thin film layers of different thickness and refractive index can be used simultaneously. So a series of thin film layers can also be used. So one thin film layer will specifically target a certain range of wavelengths. Another thin film layer below it will specifically target another layer of wavelengths. Simultaneously to decrease reflection losses to 2%. So clearly, the use of these thin films have a significant effect in improving the efficiency of these solar cells, because untreated solar cells will have a reflection losses of 40%, whereas these type of layers can reduce that, and the reflection losses can be reduced to 3% only. So this is a key aspect of a design improvement that has significantly improved the efficiency of your solar cell. Okay. Then the next efficiency improving design is light trapping by rear surface. So here the rear surface texture is made uneven to enhance randomized reflection of photons back into the cell. This makes it possible for photons to have a second pass through the junction to maximize chances of absorption. Okay. So chemical etching and just 1 second, and laser machining may be done for this. So the bottom surface, you often will have like irregular structures that are generated at the bottom surface. So this increases the local angle of incidence for the solar cells. Okay, this is say the bottom surface. So solar light is coming from the top, and since the local angle of incidence with respect to the normal is large, like this, it's getting here, and then again it gets reflected here and goes back like this. Okay. So if this was a plane surface, then the angle of incidence would have been normal, so 0. So you will have a larger chance of transmission. As you would know from basic optics, that if you increase the angle of incidence, then the amount of light that is being reflected increases, and the amount of light that is being refracted decreases. So this kind of local roughness will increase the chances of reflection back into your solar cell. Okay. So that is what is being done here. The next important part is collection efficiency. Collection efficiency. So this is defined as the proportion of radiation generated electron hole pairs that produce current in the external circuit. So what fraction of the total number of electrons and holes that are actually being collected and produce current in the external circuit? So it varies between 0.7 and 0.9. So for somewhat moderately designed cells, only 70% of the total electron-hole pairs are actually being collected at the external circuit, whereas for better designed solar cells, around 90% of it. So it's a major place for improvement of your solar cell. Okay. So we seek to prevent recombination losses within the semiconductor material. So we were trying to, what we want to do to increase collection efficiency is to prevent recombination losses within the semiconductor material. Okay. So the idea is to, so if you think of of your basic N-type and P-type semiconductor system, you have something like this. Okay. So this side is your N-type, this side is your P-type, and this is your depletion zone or space charge region, and your electrons are being generated here and moving this way, and your holes are being generated here and is moving this way. Alright. Now once these electrons are here and these holes are here, there is no further potential gradient to move these electrons and holes further. So this may spend a lot of time in this region with a flat potential gradient and recombine with any electrons that are available at the top surface here. Okay. So there can be, for example, further recombination losses if these holes and electrons are not driven further down, okay, to these places. So you can have a case that the electron will move down here or the hole will move up here because it gains excess energy through some process. All right. So so what needs to be done here in these kinds of materials, what we do is create a set of a continuously increasing dose concentrations to create potential gradients in these zones as well. Okay. So we increase the doping concentration further downstream and upstream to create a kind of a series of cascades as I will show here next. Okay. So this is the sorry about that. So this is our N side, this is our P side, and this is our primary PN junction system. Okay. Now electrons are being generated here and are flowing in this direction and going here. Okay. Now what is happening in this section? We have further doping of N plus and N plus plus. Okay, a double step system. So this area is more heavily doped than the main PN junction, and this area is even more heavily doped. Okay, so what you are getting then is these electrons, once they reach here, again fall down through this cascade and reach this zone, and then again fall down here to the N plus plus zone which is connected to the top surface. So these are collected here. So what happens is you don't have a flat profile here, but a continuous series of energy cascades with increased doping levels of N type, so that the electrons move smoothly across a series of potential gradient faults into your front contact. Okay. Similarly, on the hole side, you have holes that are being produced here, and these move upwards to here, and then these go up into a P plus zone to here. So this region is P plus dome. Okay, and this goes into the back contact. Okay, so this kind of a continuous potential gradient. So thin regions of highly doped N plus, plus, N plus and P plus material on either side of the main PN junction creates a continuous potential gradient that prevents electrons and holes from going to the wrong collector and recombine. Okay. So these are the main aspects of improving the design of your solar cell system. If you look now at the design of your solar cell, you can see why you have N plus and P plus doping at the various aspects. Okay. So why you have a P plus system, and there will be also be an N plus plus system at the top. Now we looked at for a silicon semiconductor, we looked at how we are preventing losses using various designs. But even then, we are getting around 25% efficiency at the end for an idealized silicon solar cell. Now the question is, there are other types of semiconductor materials as well, and how do they fare compared to silicon?